Hello ladies and gentlemen, good to see you again. This is the fourth lab for GGS 300 Quantitative Methods for Geographical Analysis. I hope that you've already watched the lecture, so it's the fifth lecture on probability. I would say that regarding this particular week we have probably quite a large amount of content and probably some of the most advanced content that we've needed to cover so far. So particularly in the book, you'll notice that we're basically covering 2 chapters this week. So it's quite a lot of material to get through, and therefore there's also quite a lot of concepts which we need to go through in the lectures, and also then carry out the calculations for within R and the RStudio environment in the lab. Okay, so let's begin. What you need to do is download the R script from Blackboard and then place it into a folder wherever you're running the code from, so either on your desktop or in your documents folder. And it's good if you're able to then load up the script to actually run through these examples in tandem with watching the video, and hopefully then that will provide you with a good level of understanding as to what we're actually doing in the code. And also it increases the number of hours that you spend actually using R, which is important because you need to get a lot of those hours under your belt in order for you to start to become proficient on a lot of the things that we're doing here. Okay, so let's begin. We're going to start by covering some of those basic probability calculations that we covered in the first part of the lecture. So we have a particular problem here. Imagine that every person in the world has a blood type that falls into one of 4 categories. Okay, so that's A, B, O, or AB. Now let's consider in the US that the distribution belongs essentially to 45% in the O category, 40% in the A category, 11% in the B category, and then just 4% in the AB category. Importantly, any person is able to receive their own blood type, but also the O blood type. Okay, so the question therefore is, what is the probability that a randomly chosen American can donate blood to a person with the type B blood group? Okay, so here we're interested in finding the probability of any person able to contribute to a person with this one blood group type. So we need to get the probability for B and for O. Okay, so let's just load those initial probabilities up here. So we have A, B, B, O, and in order for us to get that probability here, we're able to sum the 2 different probabilities together. Okay, so when we do that, we get 0.56, which essentially means that any chosen person has a 56% chance of being able to contribute their blood to a person with the type B blood group. So that's a very simple example of how we're able to combine those probabilities together. As we use the OR operator, we're able to sum the probabilities. Okay, let's choose a different problem now. So let's consider the distribution of blood types in India, which could be very different from the US. So the composition is 35% for the O group, 27% for the A group, 26% for the B group, and then 12% for the AB group. Okay, so what happens if you were to choose an American or an Indian at random, and what's the probability that both would have the blood type O? Okay, so in this case we're interested in what would happen if we were able to get both of these blood types, so for group O. So we need to get the American probability for type O and the Indian probability for type O. Let me just change the names here. These were residual. Okay, great. So let's just load in those probabilities first. So I'm just going to clear the ones that we've got already. So here we have all of the probabilities for the different blood groups for India. We're going to reload those ones for the US. So now we've got all of our blood groups. And in this particular case, we want to use the AND operator. And to do that, it basically means that we must multiply the two probabilities together, as we're interested in what happens if two people both had the blood type group. So there's far more degrees of freedom within this. So when we actually multiply those probabilities together, we're getting 0.1575, which is 15.75% chance that if we select one person from each country group, we essentially end up with the O blood type. Okay, so we've done the OR operator with the summation, we've done the AND operator with the multiplication, and now let's move on to a final example. So here is an example of the composition of the email spam that comes through into your email inbox. So every day there's thousands of spam messages, millions that are sent out. And essentially most of that now actually is just filtered out via your email providers. Machine learning algorithms are able to detect, based on the text pattern, for example, what the content of the message is, whether it's actually addressed to you, whether it has certain generic characteristics that indicate that it might be malicious or just junk email. And actually, if you were to analyze a lot of the composition of the emails that come through, then you might see that maybe 16% are based on some sort of financial advertisement, 7% is based on health, about 7% is also based on spam relating to leisure, 21% relating to spam related for different products that maybe people are trying to sell, and then 14% based on essentially scams or malicious content sent over the internet. And then about 14% falls into other categories. So the question is, well, what's the probability that a piece of spam does not concern one of these topics? So these don't fully represent all of the distribution. So how do we get that? Well, firstly, let's add those probabilities together into the workspace. So now we have, let me just clear this so it's definitely more of a concise example for you. So here we have all of the different types of spam that's within the composition which I presented. What we need to do is get the summation of all of these. So you see, when you add together all of the financial, health, leisure, products, scams, and other spam emails, it's only about 81% of all of the spam emails that are sent. So here we have the probability for all topics, which is 81. But in this particular case, as we're interested in the probability that a piece of spam doesn't fall into one of these categories, what we really need to get is the complement probability. So in this case, 1 would represent all of the possible outcomes. We have about 81% of the outcomes here. So to get the complement, we need to subtract the sum of all of those topics from the total amount, which is 1 here. So when we do that, we end up with about 19% probability, so 0.19 probability that essentially an email that comes through to you doesn't fall within one of these particular groups here. And you'll remember when I spoke in the lecture, I was talking about how when you have an empirical distribution, you might view the data distribution using a frequency plot, a histogram, and that's the number of observed outcomes that we have, the frequency of those observed outcomes. But we're also able to think of that in terms of the probability of future outcomes if we were to change our thinking and think not based on the past, so the observations we've got, but on the potential picks for the future. And that's why it's a really nice tool to be able to develop these different observed frequencies, which can then form probabilities for future selections from a distribution. And you'll remember that I spoke in one of the previous lectures about a piece of analysis that I'm doing at the moment on Wi-Fi access points, and how I've been developing histograms for the frequency, so the number of Wi-Fi access points in different areas. And I've basically been driving around, walking around, cycling around with various sensors, and I'm able to passively sense the number of Wi-Fi access points in those different areas. And that's really great because then you can develop these frequency plots, and we're able to build a predictive model for the future for how many Wi-Fi access points we think there are based on the building density. So I plot all of the Wi-Fi access points against the building density, and then in the future we can say, well, if there's this many buildings, we would expect there to be this many potential Wi-Fi access points, and that would could be informed based on, you know, the probabilities that we got from the observed empirical data, and you can put some sort of confidence interval on your expectation around that based on the data that you've got. So this is how these sort of quite abstract, simple calculations that we're running here could be operationalized and actually turned into, you know, real world research that informs real world decisions. So that's the basic probability section. Now let's move on to the binomial distribution. So let's just recap on what that is. So we covered this within the lecture. So the binomial distribution, it's a discrete probability distribution with only two outcomes. Remember, the hint is that it says bi, so bicycle has two wheels, binoculars has two optical viewing points. So that's the easiest way to remember that this distribution focuses on two outcomes. So it could be yes or no, true or false, success or fail, 1 or 0. Okay. And within the binomial distribution, we have a variety of conditions which need to be met. And I'm not going to go over all of these, but I do encourage you to go back to the lecture slides if you can't remember all of this off the top of your head, as what I'd quite like to go through here is the example that we covered, which is also in the book on page 82 of McGrew et al. And this is the vegetable growing problem. So you've got a site that you're interested in purchasing or renting in order to grow vegetables on it, but then you have a question over how often you might need to irrigate the field. So we have this binomial distribution function within R, which is built in. And I encourage you to just to select help and type the function into the help menu here, and it will just bring up all of the different arguments, usage details for this particular function. So you can get a density estimate, you can get a distribution function, a quantile function, or a random generation of the binomial distribution based on the arguments which you provide to it. So this is really handy, and we're going to use this here after calculating some of it manually as well. Then at least you know exactly what the function is doing underneath the hood. So there's these different arguments that you can give the binom function. So it's just the prefix, whether it uses a D, a P, a Q, or an R. And you can see these just down here. And actually the different functions are described within here, so you can get more detail if that's necessary. Okay, so let's go to the question which we were working on before. The question is, what is the probability of a grower being able to meet the requirement for irrigating only 1 in 5 years? So the site selection is important because if you're growing vegetables, the actual profit margins is could be quite small. It depends what type of crop you're actually growing. But essentially, you need to consider how often you might need to irrigate, because you might only be able to afford it based on the profit margin that you have to do this once in every 5 years. And for this particular site, the site's been fine for 21 out of 25 years. So we can get the probability of requiring irrigation as essentially the 4 years where you had to irrigate over the 25. So it's about 0.16, so 16% chance that any 1 year might require irrigation. So we're going to move this forward, and I provided you with the Excel formulae for the numerator and the denominator and some of the inputs so that you could generate this distribution here kind of by hand in Excel. So N is the number of trials, P is the probability of requiring the irrigation, X is essentially, it's a vector containing all the different outcomes that we want to test. So do you not require any irrigation, as in the case of 0? Do you require 1 year of irrigation, or 2 years of irrigation, or 3 years, or 4 years, or 5 years? And obviously the probability of those more extreme events start to become very, very small as you move up the move down the table, in this case, to the more extreme events. Okay, so let's start to play with this function. So now that we've entered those 3 different parameters here, we're able to basically get the density binomial plot for all of these different parameters that we've entered here. And you'll see that these numbers here generated by the density plot should be matching these numbers that we have down here that we calculated by hand within the Excel spreadsheet. Okay, and then we're able to allocate that distribution that we're getting to the prob x variable, which is now in the global environment up here. So we can plot these results just to see the distribution. So on the y-axis, we have the probability of this particular outcome occurring. So no irrigation, 1 year of irrigation, 2 years of irrigation, 3 years of irrigation. And these are the number of years on the x-axis here. You'll recognize that this distribution is the same as this one that I plotted just here using Excel. So I hope that by me calculating it by hand in Excel, and then also you getting an insight into how we're doing it in our studio, that gives you, a really unprecedented level of insight into how to calculate these particular metrics of interest using these relatively basic problems. Okay, so that's how we generate the distribution. Now let's actually try to put this distribution to work. So let's just say that we're interested in knowing the probability of the outcomes 0, 1, or 2 years actually occurring. So what's the total probability of any of these outcomes occurring? So if we go here, this is the manual calculation. You'll remember that we've entered prob x, so this is the vector of probabilities for each one of those years into the global environment. And actually, if we add up the 0, the 1, and the 2-year outcome, we're able to get a probability of 0.968, so it's about 96.8% chance that these outcomes will occur. Okay, so it's highly likely that you'll only have irrigation for these first few outcomes, and then the probability starts to really drop off as you get to the more kind of multi-year drought effects over a 5-year period, that is. So we calculated it manually here just by adding together those probabilities, but if we use the p-binom, we're able to get the cumulative distribution function. So here we've entered year 2, and as it's cumulative, what it's doing is it's basically saying, rather than giving me the probability for each individual outcome, 0, 1, or 2, for example, just give me the cumulative probability, so all the probabilities added together up to that one particular year. So this is how we're able to both calculate this manually and also using the function that we have here. And then when we do that through both particular approaches, we're able to estimate that it's about 96.82% chance of these 3 outcomes occurring. Okay, so let's move on then. Let's calculate the probability of needing irrigation for 3 of the 5 years. So in order to do this, we need to, I'm going to manually calculate the probability first. So this is for year 0, year 1, year 2, and year 3. Remember that these numbers here are indexing into this particular vector. So, and this just refers to the row number, for example. So actually, the probability x row 1 is year 0, and the prob x row 2 is year 1. So I just wanted to re-emphasize that. So here we're interested in the probability of needing irrigation for 3 to 5 years. Essentially what we do is we sum up the probability for year 0, 1, 2, or 3. And what we end up with is about 0.997, so that's equivalent to the cumulative probability for 3. And then what we're going to do is we're going to subtract it in order to get the complement. So down here, when we subtract that value, we get 0.0028, which obviously is very small. Okay, now let's move on and do that using the cumulative distribution function. So it's the same as before, but we're going to get the complement. So we enter year 4 into the cumulative distribution function. We subtract it from 1, and we're able to get that same probability that we're able to get as we've shown up here. Okay. And then down here we're also able to calculate the same probability again. This time we're using the p binom function. The difference is that rather than getting the complement by subtracting from 1, what we're actually doing is we are telling the function to give us the part of the distribution that we're interested in. So this time round we said that the lower tail is actually false, so we don't want the lower tail, we want everything else. And that's why it's giving us this complement probability just here. So I'm just thinking through this. This probability is actually the probability of needing irrigation for 3, 4, yes, that's correct. It's for 3 of the 5 years, so that is correct. Right. Okay, so hopefully that's given you some insight of the various different ways that we're able to obtain a probability in that way. Now let's move on to the Poisson distribution. So let's just recap on what we did on that very briefly in the lecture. So the Poisson distribution has a variety of different assumptions and expectations about why and how we should use it. So you can cover a lot of these in the previous lecture material, but essentially we're interested in measuring events that are independent and discrete. Okay, and this is the equation that we were using in order to calculate the probability of an outcome occurring, a certain number of times. So the probability of x is equal to lambda to the power of x, and it's divided by the natural logarithm, so it's the exponential of lambda. So I'll explain what this means in greater detail shortly, multiplied by the factorial of x. Okay, so that sounds complicated, but let's work it out here. So in this case, we're using the example from the book, so it's page 87. And when you read through there, what we're trying to do is calculate the number of heavy snowfall days that may take place per year. So this is for Flagstaff, Arizona. And sorry, that should say snowfall just there. So this is a real issue which local authorities or other people, public managers, will face, which is, well, how do I allocate my limited resources? And snow is always a tricky one because those places that don't get frequent snow are probably unlikely to allocate many resources to it, and often they can be quite badly hit when that does happen. So Flagstaff, Arizona actually has snow quite frequently, and as a consequence they need to work out, well, how much resource do we allocate to it here, and we're able to use this as an example to understand the number of heavy snowfall days. So we're going to explore whether there's between 0 or 6 heavy snowfall days per year. So that's what x represents. Let me just clear the global workspace here. So there we go, we have between 0 all the way up to 6. And I've just printed x down here so you can see that we've got a vector of 7 values starting at 0. When you look at the historical record, on average there's about 1.8 mean, the mean value for the number of heavy snowfall days is about 1.8. when you look at the long time series records. So this is the value of lambda that we're interested in here, the mean frequency of the event, and we can think of this in terms of well, it can be thought of in terms of future probability. What we need to do, which I mentioned before, is actually to use the exponential of lambda. I think that this was skimmed over previously, and particularly in the book, and doesn't really give much emphasis as to kind of what the exponential function is doing and why we're doing it. And I don't want to get sidetracked too much, but I just want to take 2 minutes so you understand exactly what's happening, because it's great to use the function, but you need just a little bit of background, particularly if you want to go on and use this in future work. So basically, the exponential function is using Euler's number. So E is a constant, which is otherwise known as Euler's number. And you can look this up online if you're interested. And essentially, the exponential is taking the natural log of this value E. So the natural logarithm of the value that you give it is the power to which E would have to be raised to equal x. Okay, and I appreciate when I just talk about it like that, that's quite abstract. So what I've done is I've just calculated it here in an Excel spreadsheet. So essentially our lambda value, which is mean snow days, heavy snow days, is 1.8. And all I've done in Excel is I've just taken the exponential of this particular value. So you can see here x is 6.041. So in R, if we do this for 2 or for 1, it's spitting out these numbers down here. And this is, and let's just run it for the value that we're interested in, so the lambda value. So it's spitting out these numbers down here. Euler's number is essentially 2.71828, which is a constant. And essentially what it's doing is it's saying, okay, 1.8 is the mean number of days, raise it to the power of Euler's number and give me what the answer is, and that's how it gets 6.049. So you can see it being spat out here. The problem with the functions, you don't really know what's happening. So let's take Euler's number here. So you can see I've just inputted it. So this was the automatic calculation by Excel. Here we're going to calculate it manually. So now we need to take E, which is Euler's number here. And we basically need to raise E to the power of lambda in order to get the number that we're interested in. So you can see here that I've been able to get the 6.04965 value that's being spat out of R by essentially raising Euler's number here, 2.71, to the power of the lambda value, which is 1.8. So that's this part of the calculation just here, e to the power of lambda. Okay, so we've just calculated that, using the inbuilt function, we've calculated it using the manual calculation. I hope that provides you a bit more understanding of what's actually going on. And then you can reproduce it if you want to in order to gain more understanding. Okay, so that's what happens when we get the exponential of the lambda value. So now let's return to the problem at hand, which is, well, how many snowfall days are likely? And therefore we need to calculate the Poisson distribution. So we've already done this here. So this is lambda raised to the power of x. And then we've already done this here. So this is the exponential of lambda times by the factorial. So you can get the numerator and the denominator. And then let's get the probability distribution here, which is 0.16, 0.29, 0.26, 0.16. And this is basically giving you the probability that you would have no snow days, 1 snow day, 2 snow days, 3 snow days, for example, etc., etc. Okay. You are able to look up exactly what's happening in the Poisson distribution just here. This is quite similar to the description that's already been provided for the binomial. You'll see that it has various density, distribution, quantile, and random generation functions. So you can do a lot of different stuff with it. So up here we generated this probability distribution by hand. But essentially we are able to generate the same probability distribution using the inbuilt function. Okay, so all of this, you know, we've basically been reproducing that one equation just here based on the frequency of occurrence, the mean frequency of the event, and the natural log. Sorry, the exponential of lambda, which is taking the natural log. And then we're able to produce that distribution manually. And then we're able to do that using the function that we've got here. Okay, so let's apply this to a particular problem. Let's imagine that we're sat in Yosemite and we're interested in the number of camping groups that are going to come through the national park or the local park in you know, a particular period per day. And let's say that we start by sitting there for a month and counting the number of camping groups that come through. And essentially what we get is a mean of 2.5 camping groups coming through per day. I don't know if you've been to Yosemite, but it's heavily regulated in terms of how many people are allowed in the park at once, how many days you're allowed to stay there. So you need to get a camping permit if you want to be actually going through. So you know, this is kind of a real problem which people do face, which is, you know, how do you calculate how many groups are likely to arrive, say before you implement a permitting scheme, so that you can understand how many users there might be in the park. So in order to understand what the probability of no groups arriving is, which is the question that we're interested in here, we need to specify that x is equal to 0. Okay, so x is the frequency of occurrence. Here we're interested in 0 groups arriving. So we're able to use the function specified here. This is the x value, and we're placing the lambda value, which is 2.5, also into the function. And the result that we get is 0.08, so 8% essentially chance of no groups arriving on a particular day. So that's how we would find this one particular outcome. Then what's the probability between 1 and 3 groups actually arriving? And we want to include 1 and 3. Those values need to be included. So here we're interested in x values of 1, 2, and 3. So let's run the function. What this does, so c brackets 1, 2, 3 is just specifying the vector. If you haven't seen that before, so that's just telling R that you want to create a data structure out of these. So we're able to input that straight into the function along with the mean number. And essentially when we run it, what we get is the distribution for those outcomes for 1 group, 2 group, or 3 groups. However, we don't want the individual probabilities, which is what's being returned here. We basically need to sum all of these probabilities together so that we can get the probability of between 1 and 3 groups arriving, including those values. So let's sum them up here. And when we sum them up, so 0.205, 0.56, 0.213, we get 0.675. So it's about 67.5% chance that we would have between 1 and 3 groups arriving on any one day. Okay, so that provides you with some insight on how to work with the Poisson distribution. I think this is probably an easier distribution to work with than the previous ones. It's kind of easier to calculate, and you don't need as many arguments in order to run the inbuilt function, for example, here. I mean, we're generating probabilities just by using 2 in particular arguments. Okay, so let's move on now into calculating and working with the normal distribution in order to calculate standardized scores. So we're not going to go over the specific formula here for calculating the normal distribution. What we're going to use are standard normal tables, standardized tables for those standardized values. I didn't cover this in the lecture because it was quite high level. But in the back of your textbook, if you go to page 303 on the third edition here, you'll be able to look at the statistical tables. So this is the normal table, and this gives you all of the different values for understanding the distribution of data points when you've created a standardized Z-score. Okay, so let's see what this means in reality. So we spoke about this before. The beauty of creating, these standardized scores, these relative scores expressed in the number of standard deviations, is that you're able to, regardless of how you measured the underlying distribution, whether it's kilometers or miles or reaction time in seconds, you're able to understand where a data point, for example, sits in relation to the mean or the rest of the distribution, and that's really powerful. And that's actually, it's going to be important today for how we look at using these Z-scores, but it's also going to be very important for how in the future we start to think about probability distributions and move towards inferential statistics, where we're able to say something informative about the world around us, specifically whether we should accept or reject hypotheses that we make about how the world works. Okay, so we're going to use the standard normal table based on the Z-score values that we get. A quick reminder is that the Z-score value is calculated based on the provision of a particular value, subtracting the mean, dividing by the standard deviation. So let me just show you the math for that. Here we go. We have the x-if value. We subtract the x-bar, the mean of the data set. And then we divide it by the standard distribution in order to get our standardized Z-score. And this Z-score is going to be the number of standard deviations above or below the mean value. Okay, so we can use the Z-score in the back of the book. I've actually just provided you with a link for this website online, which allows you to look up Z-scores. It also shows you how to use the Z-score table, convert a score, find the area corresponding to a Z-score, and then think about the distribution of values to draw valid conclusions. I think it's worthwhile you looking at this website as well, and just corroborating your understanding by looking at how the interpretation of these values are worded here. I think it will be a good supplement to what we're doing. And we can also use the Z-scores, the Z-score tables, the standardized tables, as we will do later here. Okay, so that's the general introduction to the normal distribution and why we're using Z-scores, the importance of it, and what we're going to do with these values. Let's think again about one of the examples from the book. So if we go to page 95, we have a 40-year annual precipitation record for Washington, D.C. When you go in, you'll see these distribution figures, so it's figure 6.3 and figure 6.4, and I think that these are important to be able to supplement graphically what we're going to cover here in the lab. So we have a 40-year annual precipitation record for DC, so it's how often, what size, what amount of rainfall has fallen over a particular year, over 40 years. The question is, well, how can we use this to make different probability estimates? So how much is likely, what chance is there of certain rainfall happening next year? And that's the type of question that we're then able to ask. Obviously, weather forecasting in general is highly informed by probability. and it's a very central concept used within weather forecasting. One of the reasons why weather forecasting has actually got a lot better over the last few years is the move to supercomputers. So we're able to get bigger computers. These are probabilistic processes, and therefore we're able to do more model runs based on the probabilities that we have. So it's called ensemble modeling. And actually, I think, at least for where I live, the weather forecast is generally much better now than it was, 10 or 20 years ago. I remember 20 years ago going away and we were expecting it was going to be a sunny day, and actually it would rain and you'd be sat there having a picnic and you'd get completely soaked. But thankfully, improvements in statistics, particularly in computing power, to enable those statistics have massively improved how we are able to do weather forecasting. Okay, so my question here is, well, what's the probability of annual precipitation exceeding 48 inches? So we know that 48 inches at the top end of the distribution, that's a lot of rain for DC to get relative to how many it gets in other years. But the question is, what's the probability of it exceeding that? So we're able to take the mean value. So this is over that 40-year period, 39.95 inches of rain have fallen on average in DC. We're able to take the xith, the xi value. So whenever I refer to the ith value, what I'm referring to is here x represents all of the observations, and the I represents observation row 1 or observation row 2 or observation row 3. So this is just an algebraic abstraction for how you refer to a certain number. And we refer to this as the ith number. So the ith, remember it could be the 4th or the 5th or the 6th number. It doesn't matter, it's just an algebraic expression. So that's why this is xi here, so for the xith number. So we're talking about 48 inches of potential rain. And the standard deviation based on the data that we have is about 7.5 inches. So that's the mean deviation, the average deviation around the mean value. So that tells us something about the shape of the distribution. And then we're able to calculate the z-score using this very simple calculation. So we're going to subtract the mean from the xith value, which we have here, and divide it by the standard deviation to get the z-score. So that's what we do here. Sorry, I haven't entered these into the workspace yet. There we go. Now I've entered them into the workspace, the x bar, the xi, the s, and then we're able to calculate this, and we get 1.073333 standard deviations above the mean. And I'm saying above the mean because it's positive, okay? So if we just did this for a very low number, say just 8 inches a year, then obviously it's going to be negative because it's going to be minus 4.26 standard deviations below the mean, okay? So let's calculate that z-score that we want, which is 1.07 here. Now we are able to look up the corresponding z-score. So we could use z-table. So if we go here, so this is the hyperlink that I've just pasted here. Now what's important when you interpret these values is you think about what the numbers in the table are representing. And that's because the tables can represent different things. So here it actually represents all of the values that fall above or below a certain point. And that's different to the standardized table which is in the back, which represents the number of values that falls between the mean and the value of interest that you have. So this is really important. So I've already emphasized this. That's, I think, why it's important to try to visualize the distribution. And that's quite nice within the book because they show you those two different graphs, and it helps you to think about where your data points are spread. So if you have the mean here, then anything that's negative is going to fall below this part here, your z-score is negative, it's going to be a value falling down here. And if it's positive, it's going to be a value that's above the mean. Okay, so the z-score in the book for this particular value is, when you look at the table, is 0.3577. So what this is representing is the proportion of the values between the mean and the value that we provide, which is 48. So when you go to the table, you need to think about how you actually interpret the values in this particular table. Okay, so for a z-score of 1.0733 here, we need to go down the y-axis and we need to find the 1.0 figure which lists the dominant number. So that's on the y-axis, and then we need to go across the x-axis until we find the 0.7, which is over here. And if you do that within the book, you can find 0.3577, okay? So this is where the number comes from in the example. I've shown you just very briefly how to interpret the Z table. This is for the one in the book. In the code here, I also show you how to do it for Z table as well. So you can also read online at how it's explained there, and hopefully that will improve your understanding. Okay, so now we know that this 0.577 value represents this part of the distribution. So from the mean value here all the way up to our 48 inches of rain just here. And it's the distance between those 2 points. Now, obviously, as this is so the quantity that's been provided to us is from the mean to the very top here. We need to subtract 0.5 in order for us to actually get the probability of all of those values that fall above the 48 inches. Okay, and I've referred you back to this figure so you can understand graphically what we're doing here. But when we do this, we end up with 0.1423, so 14% chance that in any one year the amount of rain that will fall is above the 48 inches level that we specified. So that's the way that it's done in the book, and I'd advise you to look here and to think graphically about how we do these calculations. I also just want to give you a quick understanding for how we would do that using ztable. So if you go onto ztable.com, you're able to look at the first 2 digits on the y-axis, match it to the remaining figures on the x-axis in order to find the distribution of the values. And the value that we obtain represents the proportion of values that fall above or below the given point in the distribution. And it's a different value here. It's not between the mean and the value that you've got. It's where the whole distribution falls. So it's going to be a much larger number. So in the first example I gave you, we basically got the values that fall between something like this here, just this one part of the distribution. But in the Z table, we're going to get all of the values that fall below that particular point. Okay, so from here all the way down to here. So let's do that now. So it provides you with the description. Find the values on the right of the mean in this Z table. Table entries for Z represent the area under the bell curve to the left of Z or Z. Positive scores in the Z table correspond to the values which are greater than the mean. Okay, so the value that we got is 1.0733. So in order to interpret this, we need to go down the y-axis here until we get to 1.0. So we know that we're looking at this row here. And then when we're on that row, we need to go across the x-axis looking for the 0.07, which is the next set of values in our score. Okay, so when we do that, we go from here 1.0, and then when we get to this value here, 0.8577, It's the intersect of the 1.0 and the 0.07. That's the value which represents the proportion of the values which fall below the value that we've given for the XI score, so 0.8577. And I've just reported it here for you so you know what the number is. And so you're able to look at the Z table, understand where that piece of information came from. 0.8577 represents about an 85.77% chance that a value will fall below this point. Okay, and obviously that represents all of those values below. We're interested in the number of values that fall above this, so we actually need to get the complement, so we subtract the 0.8577 from 1, which gives us the answer that we're interested in, which is 14.23%. And this matches up with the value that we got up here. So there we go. You can see now how we're able to answer this question using the information provided in the book, or also the information provided online, which uses a slightly different structure for how the results are reported. Okay, great. And here I just emphasize the fact that, you know, the structures are different. So you can look up this this function that we're going to use on the normal distribution. So we've done everything by hand up here, but the benefit is that you can just use an inbuilt function to do all of this stuff. So since we have a z-score, we don't need to provide the function with the mean or the standard deviation. We can just literally get the z-score by providing, we can get the percentage of values that fall above or below just by using, by providing the z-score to this one function. So here it's that same value again, essentially, but that indicates the proportion of the values that fall below. So we want to get the ones that fall above. So we subtract that value from 1 in order to get the 14% value that we were able to get up here. Okay, so that's how you do it automatically using an inbuilt function. So the question is, well, suppose the question's not probability, but what is the number that goes with this amount of probability? So here we've been using the relative values so far, but we're interested in actually now finding what the absolute value might be for a particular part of the distribution. So in effect, we're reversing the process. For a given probability, find the z-score. So to do this, we're going to use the quantile normal distribution function. So you can see it here, qnorm. And we're going to provide it with a probability of 0.1. So think that this is the point at which 90% of the values fall above. So we have the p-value of 0.1. We get a z-score here of minus 1.28. So this is where 90% of the values fall above. And we covered this particular problem already within the lecture. So the question was, if we know the z-score, we know the mean, and we know the standard deviation. How do we find x, essentially? So this is the absolute value at which you're able to provide some sort of confidence that the values that you get are going to be at some point within the distribution. And here I've calculated it by taking the x bar, and then what we do is we multiply the standard deviation by the z-score that we get. So for example, if the standard deviation is 3 here, and we know that the z-score is 1.6, and we know that mean is 25, then when we multiply these two values together and we add them to the mean, we get 29 in this particular example, which is the value that we wanted. So let's go back to the example that we have here within the R code. So we're going back to the precipitation example. Let's actually run the code here. So we've got x bar plus the z-score times by the standard deviation, and we're getting 30 inches of precipitation per year. So what this tells us is that 90% of the values fall above 30 inches. That can be used in future probability assessments, particularly if you want to know where a value is relative to the rest of the distribution. Okay, so that brings to a close the use of the various different distributions that we've covered within the lectures. Before we end, I'm just going to go again over the use of for loops. So we've covered these qualitatively already within the course. I've explained that a lot of this work was done, manually using a calculator 100 years ago. By calculator, I mean a very rudimentary non-digital calculator. The difference now is that we're able to use computers in order to rapidly speed up these calculations. And we've used a variety of inbuilt functions quite liberally. So we've used the sum, the standard deviation, for example, and we haven't really covered exactly what R is doing behind the scenes when it does these calculations. So let's take an example where we have a vector of values 1 to 6, and let's use 1 to 5, and here we're now able to use these inbuilt functions. So if we run the standard deviation, then we get essentially 1.581139. If we sum these values, then we get 15. So for all of the values between 1 and 5, the sum of them is 15. Well, what's actually happening behind the scenes? So what I was doing is it's looping across every one of those values in the vector. It's very easy for me to just say this, but let me show you exactly what's happening manually. Then we can look at it also in a spreadsheet in case you need some sort of a second look at how this is taking place. So let's start by saying that the sum at the very initial point is 0. This is before we do any calculations. The reason why we have to do this is more of an esoteric computer issue, which is that it's a lot more efficient to set up your variable in advance. And in some computer programs, I think in R as well, you need to set it up in advance. Otherwise, when you run the function, if you refer to this variable and it's not in the environment, it will give you an error because you don't currently have the metric available, the variable available. So let's set the summation as 0, and now let's run through a for loop. So what this is doing is saying for each value in a sequence between 1 to 5, do all the things within the curly brackets here. So when you see n, just imagine at each point in the loop it's going to loop through number 1, it's going to go through. Number 2, it's going to go through all the code. Number 3, and then all the way up to 5, so it's going to loop through everything that we put within the code. And here what we're doing is we're saying summation is 0 to begin with, and n then takes the number 1. So 0 plus 1 is 1, as I've shown manually here. And then what I'm going to do is I'm just going to print it to the command line, to the console, so that you're actually able to see the numbers that are produced at each step. Okay, so as we've already been through the first example here, it produces a 1. This is what the code is doing. You can look at these numbers here, so summation is 0, and then we add 1, we get 1. It prints it to the command line down here. And then when n takes the letter, so the digit 2, what we have is the summation is 1 plus 2, and therefore the answer is 3 as we get down here. And then it goes through this loop repeatedly, so we get a 3 plus 3 is 6, and then we get a 4 plus the existing summation 6, we get 10, and then we get a 5 plus the existing summation, which is 15. And that's how, when you press sum new and we get 15 as the total, R is actually calculating this behind the scenes. So we could do that in Excel. There we have all of the numbers that we're interested in. If we press Alt equals, we get the sum of those values, which is 15. Okay. So hopefully you can play with this function. You can start to understand exactly what's going on. I know that this seems complicated because there's multiple parts of the function, but you can also start to, if you want, you could remove parts of it and just print n. So now what we're doing is we're saying for each value in the sequence, just print it. So it's dead simple. And if you still don't understand it, do what I did there, break it down so that you're able to see each part of the function in a very simple way. Often, and I've been doing this recently, you can write a huge function maybe to visualize some data or something like that, and then you need to change it. And the problem is that you need to kind of remove the function and write in some values that you have so that you know what's happening, and then you can start to change the part of the function that you need to develop. So it can get quite complicated, but the important rule is just to go back to basics each time and remove the complexity until you're able to understand what's going on. Okay, so that's a little example there of how we calculate using a for loop or for one of the inbuilt functions. We can also think about this in terms of the binomial distribution. So this is an example here which is more complicated, but it just provides you with some insight as to how the binomial distribution changes as we change the trial number size. So you'll remember that n is equal to the number of trials. We used 5 originally because we were thinking of a 5-year period, but here we're going to change that. And what we want to do is we want to visualize the result at each iteration within the loop. So we're going to specify the line type, which we're going to start as 1, and the point type, which we're going to start as 1. And in R, you can specify up to a very large number of point or line types, and they usually take a digit number. So if you select point type 1, you might get a triangle or a square. Point type 2, you might get a cross. Point type 3, you might get a diamond. So we're able to make that change each time. Then we're able to generate a bin based on the binomial distribution. So we're giving it the number of values we're interested in, which are 20. We're giving it the number of trials, and we're giving it the probability of each outcome taking place. And we're able just to plot that down here. So 0 to 20 is the number of years that we're interested in running here. And then for each bin, we generate a probability, which you're able to see. Let's just add lines to this. And now we have a distribution function over the time period here. So this is very simple, and it's very similar to it's basically the same plot that I plotted already within the lecture and earlier within this lab. But let's just think about this where we start to use the for loop. And we add more lines to the plot to see how the binomial distribution changes as we change a certain parameter based on the for loop. So when we specify the for loop here, we're saying for n in sequence, we're going to begin with 20, we're going to end with 100, and we're going to go up in 10 increments. So the first number will be 20, the second number will be 30, the third number will be 40, and we're going to go all the way up to 100. And at each sequence, we're going to print n, so we know what's happening. We're going to add 1 to the line type and to the character type at each iteration. So we're going to get a different line type and point shape within the graph that we produce. we're going to change the bin values. So we're going to generate a different distribution, basically, based on the number of trials that we're interested in. So the n value goes in here, and this is the main thing that's happening within this for loop. This is what changes the outcome. Everything else in here is just a graphical change, essentially, to what we're going to plot. So if I run this now, you'll see that we're printing out all of those values for the sequence 20, 30, 40, 50, 60 to the console. And then what you can see is also we're plotting how the distribution changes over here on the right hand side. So this is how the probability changes as you increase the number of trials. So it was 5 initially, and that was the distribution that we plotted in the lecture and earlier on in this lab. But we're also able to change the number of trials that we get all the way up to 20, and you can start to see that the distribution shape starts to change as the probabilities spread out, for example, over the elongated trial period that we've set. We can add a legend to that and a title. So now you're able to understand the binomial distribution for different parameter values, so where we change the n value. Okay. Great, well, that's the end of this lecture. I hope it's been interesting for you. I apologise if it's been a lot of content. I think that this has probably been the most challenging week so far because we've had complex concepts, we've had lots of ground to cover. You know, we've had to cover basic probability, we've had to cover a variety of different distributional types, and then we've had to cover z-scores as well. And this is particularly grueling, I think. So if you do have any problems or you want to reach out to me, please don't hesitate. You've got, I hope that by now you've got the McGrew textbook, which the examples came from. If you've got the Simon Dadson book as well, then that's great. That's extra reading, and it's a very nice book for how they explain a lot of these concepts. There's a lot of content available on YouTube if you need further material to help solidify this. I hope that by presenting the calculations in a variety of different ways, both theoretically in the class using math, and then also calculating it manually and using functions in R, and also using Excel to calculate these, you've been able to see how there are commonalities in the way that we produce these numbers. And that's hopefully going to put you in good stead for how we move forward in the course, particularly as we go towards inferential statistics towards the second half of the semester. Okay, well, thank you very much for tuning in. Let me know if you have any questions, and I'll look forward to seeing you again soon. Thank you.